Okay, next topic is the quadratic forms. The definition of quadratic forms is this. Consider a, let's just use the simplest case. Consider a two-dimensional vector x. So your x is x1 and x2. And consider a 2 by 2 dimensional square matrix A. A is A, B, C, D. For the moment, let's just assume that it's symmetric. So the matrix here is symmetric. Okay. Then a quadratic form, it has the following form. So your x prime A x is a quadratic form. Okay, what is this? So this is x1, x2 prime, A, B, B, D, and x1, x2. Now this becomes A x1 plus B x2, comma B x1 plus D x2 and x1 x2, which becomes A x1 squared plus B x1 x2 plus B x1 x2 plus D x2 squared, which is A x1 squared plus 2B x1 x2 plus D x2 squared. So a quadratic form is a matrix representation of a quadratic equation, right? Okay, what you know is consider the following quadratic equation. A x1, so your z is A x1 squared. Let's change the notation. Instead of A, I'm going to use a capital letter here. So A x1 plus B x1 x2 plus C x1 plus D x2 plus x2 squared E x2 squared E x2 squared plus some constant f. So a most general form of a bivariate quadratic equation is this. You can change this into the following form. You can change this into x 1 squared can change this into some z equals to x1 minus A x2 minus B prime. Instead of A, let's just change mu1 mu2 A B B D x1 minus mu1 x2 minus mu2. Okay, so find out what these parameters mu1, mu2, a, b, d, mu r and z are in terms of a, b, c, d, e, f. Okay, so intuitively speaking, there are 1, 2, 3, 4, 5, 6 coefficients in the original form, but here as well 1, 2, 3, 4, 5, 6 parameters in the changed form. So you can intuitively see that these parameters in the new form is related with the parameters in the original form. So the task here is to find how they are related. The point here is, that's up to you. Okay, that's up to you. The point here is this general bivariate quadratic form can be transformed into a quadratic form. Okay, so quadratic form in a matrix is a matrix representation of a quadratic equation. If you have more variables, like 3 variables, you can write the quadratic form as follows. Some z equals to x1, x2, x3 minus mu1, mu2, mu3, and a, b, c, d, e, f, d, e, f prime x1, x2, x3 minus mu1 minus mu2 minus mu3. Okay. Since it is not easy to visualize the trivariate function, so let's just stick to the bivariate case. Okay, in the simplest form, a quadratic function is this, like I wrote, x1, x2 prime a, b, b, d, x1, x2. That's a quadratic form, and depending on the value that you assign to this quadratic form, this may look like this. Okay. Before we move on, you may wonder why the matrix in the middle has to be symmetric. Actually, it doesn't have to be, but you can symmetrize the matrix, because consider the following quadratic form: x1, x2, a, b, c, d, x2, x1, x2. Okay, this becomes x1 squared plus b plus c x1 x2 plus d, so ax1 squared d x2 squared. So mathematically this can be rewritten as x1 x2 prime a 2 b plus c over 2 b plus c over 2 d x1 x2. So since the results are always the same regardless of what the b and c are, you can see that we don't need to consider this case, right? We don't need to consider this case because the matrix in the middle can be symmetric. We can make that matrix a symmetric matrix. Okay. All right. Can you visualize this quadratic form? Let's think about the simplest case. Consider identity matrix. Then this becomes x1 squared plus x2 squared. So when z is 0, when z is 0, it's the origin. x1, x2. So when z is 0, it's the origin. So the set, let's consider a set C of z is x1, x2 such that x1, x2 prime 1, 0, 0, 1, x1, x2 is z. So C of 0 is 0, 0. What about C of 1? C of 1 is the set such that x1 and x2, that x1 squared plus x2 squared is 1. That's a circle. Right? That's a circle. What about C of 4? C of 4 is a circle with radius 2. Okay. All right. So the quadratic form creates a circle when the matrix in the middle is an identity matrix. What about this one? Okay. Now this, because it's a circle, you can see that x1, x2 prime 1, 0, 0, 1, x1, x2. The value of this quadratic form is always greater than or equal to 0, and this is 0 if and only if x1, x2 is 0, 0. If the quadratic form of this matrix satisfies this property that the value is always greater than or equal to 0, and is 0 only if the vector here is the origin, then this matrix is called positive definite matrix. Positive definite matrix. There are other positive definite matrices. For example, consider a matrix, the following matrix. So now let's say your A is 2, 0, 0, 1. Then the quadratic form x1, x2 prime 2, 0, 0, 1, and x1, x2 is 2 x1 squared plus x2 squared. Okay. Then that's always greater than or equal to 0, and is 0 if and only if x1, x2 is 0, 0. So this is another example of positive definite. Now what about this matrix? What about what about 2 1 2 1, then x1 x2 2 1 1.5 1.5 1, then x1 x2 prime 2 1 over 2 3 over 2 3 over 2 1 x1 x2 is x1 prime x1 2x1 plus 2 over 3 x2 comma 2 over 3 x1 plus x2 and x1 x2, then it's going to be 2 x1 squared plus 2 over 3 x1 x2 plus 2 over 3 x1 x2 plus x2 squared, then it's 2 x1 squared plus 3 x1 x2 plus x2 squared, then it's going to be 2 x1 plus x2 and x1 plus x2, right? So it's not always greater than or equal to 0, right? This is so hold on, let's change this a little bit. Let's make it to a complete quadratic equation. So 2 x1 squared plus 3 over 2 x1 x2 plus 4 over 3 x2 squared minus 4 x2 squared plus x2 squared, then it's going to be 2 x1 plus 4 3 x2 squared minus 9 over 16 8 x2 squared plus x2 squared equals to 2 x1 plus 4 over 3 x2 squared minus, so am I doing it correct, 1 over 8 x2 squared. So depending on x1 and x2 values, it can be positive, it can be 0, it can be negative. So not every matrix is a positive definite. But there is another category, another interesting category of such matrices, which is positive semi-definite. So consider this matrix. Then the quadratic form of the matrix is x1 plus x2, comma x1 plus x2, x1, x2, which is x1 squared plus two x1 x2 plus x2 squared, which is x1 plus x2 squared. So this is always greater than, the value of this quadratic form is always greater than or equal to 0, right? But unlike the positive definite case that we discussed, this is 0 if x1 is minus x2. So there are many cases that the value of quadratic form is 0, not just the origin. If the matrix has this property, this matrix is called positive semi-definite. Okay, positive semi-definite. Now, let's get back to the positive definite case that we discussed. And I'm going to draw a diagram. So now your A is this 2 0 0 1. We know the quadratic form of this matrix A is 2x1 squared plus x2 squared. What is the graph of this? What is the shape of this graph? What's the shape of this graph? If you recall, this is x1 squared over this is x1 over square root 2 over 1 squared plus x2 squared. Okay, and bring the z to the other side, you get this square root 2 over z then this set the C of z such that x1 x2 is x1 x2 quadratic form of the matrix is mathematically x1 x2 such that x1 over square root 2 over square root z squared plus x2 over square root z squared equals to 1. Right? And you may recall you may recall here your z is greater than 0. You may recall a formula for what? For an ellipse, right? So formula, this is an ellipse, right? This is an ellipse, and here the ellipse is, this is your x1, this is your x2, and it's an ellipse, right? So from this exercise, you can see that a positive definite matrix creates an ellipse. If z increases, then the ellipse has a bigger shape. If z is smaller, then ellipse has a smaller shape, but it's an ellipse. On the other hand, the semi-definite matrix, the quadratic form of this semi-definite, positive semi-definite matrix is going to be a line, right? So it's a line. It is depending on z. It's like this, right? Now visualize a three-dimensional space. Here's your x1 axis, x2 axis, and here's your z. So when a is positive definite, then for z is 0, it's a point. For z is 1, it's an ellipse. It's an ellipse. For z is 2, it's a bigger ellipse. Okay. So it's going to be a shape like a ball. In this three-dimensional Euclidean space. When a is positive semi-definite, however, when z is 0, x1 plus x2 is 0. So it's going to be a line. Let's change the color here. It's going to be a line like this. When z is 1, it's going to be x1 plus x2 is 1, or x1 plus x2 is minus 1. So it's going to be two lines here, this line, or this line. So by changing that continuously, you can see that it's like this. Right? The three-dimensional shape of this quadratic form gives you a valley-like shape. It's a valley-like shape. And the line here, this line here is x1 plus x2 is plus minus square root z. Okay. Now the quadratic formula have an important role in minimization problem. But before we get into that part, let's see how the quadratic form and eigenvalue decompositions are connected, related. So let's consider positive definite matrix like 2 and 0. So here now x1, x2 prime and positive definite matrix. Positive definite matrix. Let's make a general positive definite matrix. A and x1, x2. This is a quadratic form. An interesting feature of a positive definite matrix is you can do eigenvalue decomposition of A. So you can do this x1, x2 prime, and you have this matrix P, and you have this matrix lambda, and you have this matrix P prime, and x1, x2. Okay. This P and P prime has very interesting feature. P prime is P prime. P is identity matrix. So P prime is the inverse of P. When the transpose is the inverse of P, is called the Hermitian. So P here is a Hermitian matrix, and by construction, when you create this P matrix, you normalize, right? So if you studied the eigenvalue decomposition part, when you create a matrix P, what you do is you normalize the matrix. So every column of the P has length 1. So let's say your P is P11, P12, 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 P21, P22. Then what we know is P11, P22, the norm is 1, and P 12, P22, the norm is 1, and when A is positive semi-definite, positive definite, positive semi-definite as well, actually, the P is orthonormal. So what it means is P P11, P22, P21, sorry, P21, P21, inner product P12, P22 is 0. Okay. So this matrix becomes let's do this operation first. x1, x2 prime p lambda and p prime x1, x2. And this is actually p prime x1, x2 prime lambda p prime x1, x2. Let's define v1, v2 as p prime x1, x2. Then this becomes v1, v2 prime lambda v1, v2. So now the quadratic form of matrix X becomes quadratic form of matrix lambda for this variable v with this vector v. Okay, what does this do? So here p prime x1, x2 is P1, P11, P21, P12, P22, x1, x2, which is P11, P11 plus P12, P11x plus P11 x1 plus P12 x2 and P21 x1 plus P22 x2. Okay, so suppose here's your x1, so consider here's your x2. So this point here is x1 and x2. Okay, and put some numbers here and verify that the changed this matrix operation, the multiplication of the matrix to this vector makes new vector like this, which has the same length. Okay, so this matrix, the P matrix, what P matrix does is it rotates. Depending on the values, of course, it rotates this way or this way. But what the point here is, it doesn't change the length. Okay, it simply rotates. So in V1, V2 space, it's gonna be the same length. Okay. and we know the v1 v1 v2 prime lambda v1 v2 is an ellipse. One more thing to mention, I should have mentioned, is when your matrix is positive definite, then the eigenvalues are always positive. So the lambda has this form lambda 1, lambda 2, 0, 0, where lambda 1 is greater than 0, lambda 2 is greater than 0. So here this quadratic form in terms of v space becomes lambda 1, lambda 2, 0, 0. So as we have seen before, this depending on the magnitude of lambda 1 and lambda 2, this quadratic form creates an ellipse. Now, what then is the quadratic form? What graph the quadratic form in terms of original vectors x1 and x2 and a creates? So the p rotates the thing. So in the original form, x1 x2 prime a x1 x2 is going to be p prime x1 x2 and lambda and p prime x1 x2. So, and the rotated shape is an ellipse in this v1 v2 axis. So before the rotation is going to be this, right? So in the new axis here, this is going to be the graph of the quadratic form of A in x1 and x2 axis, right? Okay. So, in the section, quadratic form section number 13, I've covered these contents, these things, and mentioned a few interesting and important properties of positive definite and positive semi-definite matrices. So, read that part. And I'm gonna continue with multivariate calculus in the next lecture.